Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Stationary State Wave Functions of Hydrogen Atom from the paper Quantum Mechanics. So, students, let us see what we are going to study in this module. First, we will learn how the analytic expression for the radial functions of hydrogen-like atoms, they are derived from the given second-order differential equation. Next, we will study some typical properties of associated Laguerre polynomials in terms of which the radial functions of hydrogen atom they are expressed. Next, we will also discuss about the radial functions of hydrogen atom that can also be expressed in terms of the confluent hypergeometric function which are related to the associated Laguerre polynomials. We will also learn some important properties through the plots stretched for few low values of quantum numbers NL of the radial functions and their density distributions. Lastly, we will study the analytic expressions for the expectation values of K for lower values of K, that is 1, 2, 3, minus 1, minus 2, minus 3 between the radial functions. So students, let us start with a basic introduction about the module. This module is in direct continuation of the preceding module where we have studied the eigenvalues of hydrogen-like atoms. Now here we shall focus on the radial functions. We shall see how the differential equation for the hydrogen atom, which is derived from the earlier, admits of physically admissible solutions which can be expressed in terms of the associated Laguerre polynomials. So, having studied the important properties of the associated Laguerre polynomials, we shall find that these are also related to the confluent hypergeometric functions in terms of which the radial functions of hydrogen atom can also be expressed. For few low values of the quantum number NL, the radial functions are explicitly written and their plots are presented depicting the typical properties of the radial functions and their distributions. Now finally, the expectation values of r to the power k between the radial functions of hydrogen atom, they are also recorded. Radial eigenfunctions in terms of Laguerre polynomials. Radial eigenfunctions of the bound states. In the preceding module, we obtained the differential equation for the function g rho, which is given by rho d square by d rho square plus 2l plus 2 minus rho multiplied by d rho plus lambda minus L minus 1, this whole multiplied by g rho equal to 0. We have found that in order to have an admissible asymptotic behavior, the function must be a polynomial. So in fact, the physically admissible solutions of g rho corresponding to lambda equal to n may also be expressed in terms of what are known as associated Laguerre polynomials. To see this, let us define the Laguerre polynomial LQ rho by the relation LQ as a function of rho equal to exponential rho multiplied by dq by d rho q of rho to the power q exponential minus rho. And note that these Laguerre polynomials u as a function of rho s equal to exponential of minus rho s divided by 1 minus s, the whole divided by 1 minus s equal to summation over q equal to 0 to infinity LQ rho divided by q factorial multiplied by s to the power q, where s, the modulus of it, is less than 1. So differentiation of this generating function with respect to s yields the recurrence formula, that is LQ plus 1 rho plus rho minus 1 minus 2q multiplied by LQ rho plus q square L q minus 1 rho equal to 0. Similarly, upon differentiating of u rho s with respect to rho, we find that d by d rho of LQ rho minus q multiplied by d rho of LQ minus 1 rho plus q multiplied by LQ minus 1 rho equal to 0. So using equations 26.4 and 26.5, it can be easily shown that the lowest order differential equation involving only LQ rho is rho d square by d rho square plus 1 minus rho d by d rho plus q, this whole multiplied by LQ rho equal to 0. So now we define the associated Laguerre polynomials by the relation LQ p as a function of rho equal to dp by d rho p of LQ rho. Associated Laguerre polynomial and radial eigenfunctions. Now differentiating the equation 26.6 by p times, we find LQ p rho satisfies the differential equation, that is rho d square by d rho square plus p plus 1 minus rho multiplied by d rho plus q minus p, the whole multiplied by LQ p rho equal to 0. So associated Laguerre polynomial and radial eigenfunctions On putting lambda equal to n in 26.1 and comparing this with 26.8, we find that the physically admissible solution G rho of 26.1 is given up to a multiplicative constant by the associated Laguerre polynomial Ln plus L 2L plus 1 rho, where we have Q is equal to n plus 1 and P is equal to 2L plus 1. Note that this polynomial is of the order n plus L minus 2L plus 1 equal to n minus L minus 1 equal to n in accordance with the relation already explained or obtained in the preceding module. Thus, the radial solution R ln rho for a given n can be expressed as R ln rho equal to n nl rho to the power L exponential minus rho by 2 multiplied by L n plus L 2L plus 1 as a function of rho. So using the relation 25.17, 25.18 and 25.34, we can also relate rho to R in terms of rho equal to 2z by Na mu multiplied by R equal to 2z by Na naught multiplied by mu by m multiplied by R. So the choice of the normalization constant of the function is obtained using the property integral 0 to infinity exponential minus rho multiplied by rho to the power L plus 1 multiplied by L q p rho to the power 2 dq is equal to 2q minus p plus 1 multiplied by q factorial to the power 3 divided by q minus p factorial. So equation 26.10 may be verified with the help of generating function for the associated Laguerre polynomials, which may be obtained by differentiating 26.3 p times with respect to rho, that is up as a function of rho s equal to minus s to the power p exponential minus rho s divided by 1 minus s, the whole divided by 1 minus s to the power p plus 1 equal to summation over q equal to p to infinity over LQP as a function of rho divided by q factorial multiplied by s to the power q, where the modulus of s is less than 1. Relation of Laguerre polynomials with hypergeometric functions. Using equations 26.9 and 26.10, we get the radial functions R and LR with the normalization, the integral of modulus of R and LR the whole square, R square dr equal to 1 as R and LR equal to minus the square bracket 2z by Na mu the whole cube multiplied by n minus L minus 1 factorial divided by 2n multiplied by n plus L factorial the whole cube, the whole to the power 1 by 2 multiplied by exponential minus z by n a mu multiplied by r, this multiplied by 2zr by na mu to the power L multiplied by L n plus L 2L plus 1 of 2zr by Na mu. Alternatively, physically admissible solutions of G rho given by 26.1 can also be expressed by the confluent hypergeometric function, that is 1f1 as a function of L plus 1 minus n to L plus 2 rho, which are related to the associated Laguerre polynomials by a multiplicative constant, which is given by L n plus L 2L plus 1 rho equal to minus n plus L the factorial the whole square divided by n minus L minus 1 factorial 2L plus 1 factorial, this whole multiplied by 1f1 as a function of L equal to 1 minus n 2L plus 2 rho. Expressions for first few radial functions. Thus, expression 26.13 can also be written as Rnl rho equal to 1 by 2L plus 1 factorial multiplied by 2z by n a mu to the power 3 multiplied by n plus L factorial divided by 2n multiplied by n minus L minus 1 factorial to the power 1 by 2. This multiplied by exponential minus rho by 2 multiplied by rho to the power L multiplied by 1f1 as a function of L plus 1 minus n 2L plus 2 and rho. So explicit expressions for the first few radial functions. Thus the complete eigenfunctions of the discrete spectrum for hydrogenic atoms may be written as psi nlm as a function of r theta phi equal to r nlr ylm as a function of theta and phi with the normalization condition 0 to infinity r square dr multiplied by 0 to pi sine theta d theta multiplied by 0 to 2 pi d phi multiplied by the modulus of psi nlm r theta phi the whole square equal to 1. The first few radial functions, the for n equal to 1, 2, 3 are given here, and r10 as a function of r equal to 2 multiplied by z by a mu to the power 3 by 2 multiplied by exponential of minus zr by 2a mu, and r20 as a function of r is given by 2 multiplied by z by a mu to the power 3 by 2 multiplied by 1 minus zr by 2a mu multiplied by exponential minus zr by 2a mu. Now r21 as a function of r equal to 1 by root 3 multiplied by z by a mu to the power 3 by 2 multiplied by zr by a mu multiplied by exponential of minus zr by 2a mu, and r30 as a function of r is equal to 2 multiplied by z by 3a mu to the power 3 by 2 multiplied by 1 minus 2zr by 3a mu plus 2z square r square by 27a mu square, this whole multiplied by exponential minus zr by 2a mu. r31 as a function of r is equal to 4 root 2 by 9 multiplied by z by 3a mu to the power 3 by 2 multiplied by 1 minus zr by 6a mu multiplied by ZR by A mu. This is multiplied by exponential of minus ZR by 2A mu. Now R32 as a function of R is equal to 4 by 27 root 10 multiplied by Z by 3A mu to the power 3 by 2 multiplied by ZR by A mu the whole square multiplied by exponential of minus ZR by 2A mu. From our earlier study, we know that the quantity, the modulus of psi NLM r theta phi the whole square dr equal to psi star NLM r theta phi psi NLM r theta phi r square dr sine theta d theta d phi represents the probability of finding the electron in the volume element given in spherical polar coordinates by dr vector equal to r square dr sine theta d phi when the system is in the stationary state specified by the quantum numbers n, Lm, while the position probability density psi NLM r theta phi the whole square dr vector equal to the modulus of RNLR the whole square 2 pi to the power minus 1 multiplied by theta NLM as a function of theta the whole square does not depend on the coordinate phi. It is the product of the angular factor 2 pi to the power minus 1 multiplied by theta Lm as a function of theta the modulus the whole square and of the quantity RNLR modulus the square which gives the electron density as a function of r along a given direction. So the radial distribution function, that is dNLR equal to r square multiplied by the modulus of RNLR the whole square. This gives the probability per unit length that the electron is found to be at a distance r from the nucleus. Now students, these are the graphs or the plots of the radial functions RNLR and radial distribution functions r square RNLR square versus r for the quantum numbers NL corresponding to 1 0, 2 0 and 2 1 for atomic hydrogen atoms. On integrating 26.17 over the polar angles theta and phi and using 26.14 we find that integral from 0 to pi over sine theta d theta multiplied by integral 0 to 2 pi over d phi multiplied by psi NLM r theta phi modulus the whole square multiplied by r square dr equal to r square multiplied by RNLR the modulus the square dr multiplied by 0 to pi d theta sine theta multiplied by integral 0 to 2 pi d phi multiplied by YLM theta phi modulus the whole square equal to r square modulus RNLR the whole square dr equal to dNLR dr represents the probability of finding the electron between the distances r and r plus dr from the nucleus, which is independent of the direction. We are shown a few more radial functions and radial distribution functions for few values of NL. So these are the radial functions R, NL, R, and radial distribution functions R square, R, NL square, R for a few values of quantum numbers NL corresponding to 30, 31 and 32. Striking features. Some of the interesting features emerging by observing the plots of the radial functions and the radial distribution functions can be summarized as: first, only for S states, that is L equal to 0, are the radial eigenfunctions different from 0 at R equal to 0. We also find that since y00 equal to 4 pi to the power minus half is independent of theta and phi, so one can see the equations 26.14 and 26.13, that is psi n00 as a function of 0 modulus the whole square equal to 1 by 4 pi Rn0 as a function of 0 modulus the whole square equal to z to the power 3 divided by pi a0 cube multiplied by n cube. Moreover, each of the S state radial eigenfunction Rn0 are such that at R is equal to 0, the derivative of Rn0 with respect to small r is not equal to 0. So this behavior is due to the fact that the potential energy is infinite at R equal to 0. Now the second fact is that it can be verified from equation 26.13 that the radial eigenfunction Rnl as a function of small r are proportional to r to the power L near the origin as expected from our earlier discussion. So thus, for L not equal to 0, the radial wave functions remain smaller over distances with increase with L. So this behavior is due to the presence of the centrifugal term L multiplied by L plus 1 h cut square divided by 2 mu r square contained in the effective potential. Now the third striking feature is that the associated Laguerre polynomial, that is capital L, n plus L, 2L plus 1 as a function of rho is a polynomial of degree nr equal to n minus L minus 1 having n as the radial nodes 0. So thus the radial distribution function dnl as a function of small r has n minus L maxima. Also, it may be noted that there is only one maximum when for a given n, the orbital angular momentum quantum number, that is small l, has its largest value, that is small l equal to n minus 1. In that case, nr equal to 0, and from 26.13, we see that Rn n minus 1 as a function of small r is approximated to r to the power n minus 1 exponential of minus zr by n a mu. Thus, dn n minus 1 r equal to r square multiplied by capital R square in n minus 1 as a function of small r will show a maximum at a value of r obtained by solving the equation d capital D n minus 1 r divided by dr equal to 2nr 2n minus 1 minus 2z by na mu multiplied by r to the power 2n, this whole multiplied by exponential of minus 2zr by na mu equal to 0, which gives r is equal to n square a mu by z. Now the second point is that we may also note that all the hydrogenic bound state wave functions of the form 26.14 transform under parity operations as P psi NLM R theta phi equal to P R NL R Y LM theta phi equal to R NL R P Y LM theta phi equal to R NL R minus 1 to the power L Y LM theta phi equal to minus 1 to the power L R NL R Y LM theta phi equal to minus 1 to the power L psi NLM R theta phi. Thus, hydrogenic states under parity transform as minus 1 to the power L. Expectation values of R to the power K. So now this table given below, we have recorded the mean value of R to the power K, that is for K equal to 1, 2, 3, we have these particular values of the mean values of R to the power K. Now students, as you can see here, if the K value is minus 1, minus 2, minus 3, then the average value of R to the power K is also being tabulated. So students, let us summarize what we have learned in this module. First, we have learned how the analytic expression for the radial functions of hydrogen-like atoms are derived from the given second-order differential equation. Second, we know some typical properties of the associated Laguerre polynomials in terms of which the radial functions of hydrogen atoms are expressed. Thirdly, we know that the radial functions of hydrogen atom can also be expressed in terms of confluent hypergeometric functions which are related to the associated Laguerre polynomials. Next, we learned some important properties through the plots sketched for a few low values of quantum numbers NL of the radial functions and their radial distributions. Next, we also learned the analytic expression for the expectation value of R to the power K for lower values of K, that is 1, 2, 3, minus 1, minus 2, minus 3 between the radial functions. Thank you.